Good morning, I am Lorenzo Venello and I will present our work in human posture prediction for human-robot collaboration. During my thesis, I investigated how collaborative robots could be used to optimize human postures during a collaborative task. The main problem I encountered since now is that the human is not controllable. In fact, in many cooperation tasks, like transportation, the robot could only modify the human end effector position. The human body, from the other side, is overactuated. It means that for a same end effector pose, several postures are possible. For this reason, it is necessary to estimate the most probable human posture associated to the robot end effector pose. In this paper, we try to propose a method to assess the human posture in collaborative tasks. The work born in the context of the AHFE project. The main aim of this project is to improve the quality of the human work using intelligent collaborative devices. In particular, during my thesis, we are focusing on the use of collaborative robots in industrial scenarios. Previous works showed that collaborative robots could be used to reduce human physical efforts and improve the ergonomics of the movement. This is an important factor in industrial scenarios because it could be used to reduce musculoskeletal disorder, which currently are the second cause of disability worldwide. Ergonomics core typically rely on kinematic and dynamic information. These are mostly related to the human posture, to the action executed, and to the interaction with the environment. To model some of these aspects, several digital human models have been proposed. A digital human model is a humanoid robot which tries to approximate the human posture as much as possible. In online applications, usually the digital human model is designed as a rigid body model, with a limited number of degrees of freedom. This kind of model is fast to simulate, while it allows to represent several human-related measures. One key aspect of human-robot collaboration is how to predict the human response to a robot trajectory. The answer to this question is not straightforward because a human could do the same end effector movement in several ways. For instance, to collect an object from a table, we can keep the back straight or bend it. And the same applies to the other joints involved in the movement, such as the shoulder and the elbow. In this paper, we propose an approach to predict how the human will respond to a given end effector trajectory. To do that, we hypothesize that the human and the robot are physically coupled, the human operator follows the robot, and the human posture is known at the initial time step. Given this hypothesis, we propose an algorithm for predicting the human posture in such a way to consider the human preferences in the movements. Our approach has the three following advantages. First, it is a probabilistic approach, so it returns a distribution over the possible human postures where the probability is associated with personal preferences. Second, it is a kinematic aware, so it uses the digital human model to pass from the end effector pose to the joint posture. Third, it is geometrically aware because all the postures returned by our algorithm have the same end effector pose. The method we propose is composed by two parts. In the first part, we train a model to fit the human preferences using a dataset of demonstration. These demonstrations have been retargeted to a digital human model and used to derive the new space velocities. New space velocities are joint velocities which don't influence the end effector velocity. At this point, machine learning algorithms, like Gaussian processes, have been used to fit the human preferences and to predict unexplored movements. In the second part of the framework, we use the learned model to predict the human joint trajectory given the robot end effector trajectory. The framework has been tested in several setups. First, on a simulated 5-hour planner robot to test the validity of our algorithm, and then on 3 human-robot interaction scenarios. The results show that the algorithm could be used to predict the human postures and has better accuracy with respect to the other model-based algorithms. Meanwhile, the solution proposed satisfies the kinematic constraint, allowing a safe collaboration. The algorithm has been integrated in a simulated environment to visualize the effect of a given robot trajectory. In this video, we can observe how while we are moving the robot and the effector, the digital human model could assume different postures. In the simulation, the left arm of the digital human model has been raised to improve the visualization quality. One important aspect of predicting a probabilistic distribution over the human postures is that it allows access to a probabilistic estimation of the human ergonomics score. We evaluated the posture using some of the state-of-the-art methods for ergonomic scoring, like Rula, Rula Continuous, RIBA, and cumulative back angle. In future works, we would like to integrate our framework in a human-robot collaboration setup to optimize the human postures during co-manipulation tasks. So, resuming, in our work we presented a framework for estimate a probabilistic distribution over the human postures given the robot and effector pose. We evaluated our method on many human-robot collaboration scenarios. Moreover, we used the proposed method to assess to a probabilistic estimation of the human ergonomic scores. In future, we would like to integrate the proposed method in a human-robot collaboration setup to optimize the human postures during the collaboration. Thank you for your kind attention. I remain available for any questions.